I guess today I requested some backup, as this is a very technical topic. Yesterday we covered some of the basic topics of load pole, waveform engineering, harmonic, basic fundamental tuning, things like that. Today we're going to really look at more advanced concepts of of harmonic tuning, not just on the output but on the input. Look at waveform engineering more into detail. And for that, we basically asked the help of Dr. Tushar Sharma, who basically has done lots of work with us in the past years. So there's, Tushar wasn't alone on this. He had a whole, team working with him. Basically, he did some work with Sagardar, Professor Fidel Ganucci. Also, an acknowledgement to Damon Holmes at NXP, who was very instrumental in this work. I've worked with Tushar quite, a few years now, and he always has these advanced concepts that he wants to do and push the envelope of load pull. And, if I go back a bit in time, say probably like 10, 15 years ago, the concept of waveform engineering was kind of still in its infancy. And people were like, they knew it and understood it, but, it was far from being implemented in the lab. Some people would kind of look at the waveforms and would do source tuning, harmonic source tuning and things like that, but nobody really grasped the concept of how that was really behaving at the device plane, at the waveform, in the waveform domain. So, it was more like, oh, I'm tuning the fundamental impedance at the source. I'm seeing some sort of behavior. And then when I tune the second harmonic impedance, oh, I'm also getting some better or some worse performances. But nobody could really understand this, adequately. So, Tushar really tackled this topic, and in this paper, he'll go really into the details of how to improve the performances of an amplifier. So on that note, Tushar, the stage is yours.
Hey, thank you, Vince, for the introduction, and it's my pleasure talking today to people all around Europe. So this work was my PhD work, which was basically done in collaboration with the NXP Semiconductors and Focus. I also have one called Sagar Dhar, who is a PhD student who is finishing his PhD. So a part of the research is part of his PhD as well. So I will be walking through the fundamentals and then how we utilize the fundamental mathematics and understanding to validate these advanced concepts using harmonic load pull. So to start with, we know that power amplifier classes, broadly, depending on harmonics, we can classify it into two types. On the left, we see if our higher order harmonics are short, then depending on the bias, we have been defining classes of operation like class A, AB, class B, and class C. Now, if we start playing with the harmonics second or third, then things change. And then class J, class F, inverse class F, depending on the combination of harmonics, whether second is short or second is open or vice versa, different classes of harmonic tuned PAs can be defined. So just to be clear, even for harmonic tuned PAs, there can be different bias points. There can be a class A bias class F or a class B bias class inverse class F. But the point here is that broadly, if we start moving our harmonics, the definition mostly fall into the right-hand side where we have class F, inverse class F, and then there are some new classes of operation which was published by us like class GF and GF-1. And if you see the trend, depending on waveform shaping, the idea is to shape the waveform at the drain with minimum overlap between voltage and current so that we can maximize the efficiency. So I will be walking through some of these advanced classes, starting from the fundamental classes, and then we'll be showing how we validated these classes and some advanced concept using harmonic load pull. Next. So going to the fundamentals, we guys are aware of a conventional class A amplifier where we have a full sinusoid voltage waveform and a current waveform. And in class A amplifier, there is a maximum overlap between voltage and current. And as a result, the efficiency is quite low, and the maximum efficiency we get under class A amplifier is around 50%. So the class A amplifier is mostly used for linear applications, for like example in audio amplifiers. It's a relatively a linear amplifier with low efficiency, and it has been discussed quite extensively in the literature. So moving next, if we change the bias condition and bias our device under class AB bias of operation, the major thing what happens is that the voltage is still the same, but the current clipping starts, and my current conduction angle basically varies from 180 degrees to 360 degrees between that, and my efficiency can go anywhere, can swing anywhere between 50% to 78.5%, which is the extreme end of class AB or deep class AB, which we also call as class B amplifier. So moving next, the most popular class, which we have been working around, have been used quite extensively in advanced modulation architectures, are mostly like class AB and class B bias. In class B bias, the current waveform is half sine, which means that my current waveform has the even harmonics, and my odd harmonics here are basically, I have no odd harmonics in my current waveform, and the voltage is still same. So from class A, class B to class AB, voltage has always been a sinusoid wave, but my current waveform changes, and current waveform is also changing in a way that my conduction angle is changing, and due to that my overlap changes in all these classes. So with this, the maximum efficiency we can extract in a class B mode is around 78.5 theoretically. We can compute it based on the current harmonic components. So from this bias dependency of the conventional classes, we move into more advanced classes now. Like for example, class F. Now class F is interesting. Like if you take a class F which has infinite harmonics, then it means my even order harmonics are short and my odd order harmonics are open. So if we design that kind of a class F amplifier, we technically are aiming for 100% drain efficiency, because there is zero overlap between voltage and current. But practically speaking, those things are not valid in the real world, and we cannot do much above 3 harmonics, especially, now the frequencies are moving up from 1.8 to 2.6 to 3.5 for sub 6 gigahertz applications. So we can limit our voltage, and the voltage is defined as given in the expression here. And the voltage is kind of a square-like voltage, limiting it to 3 harmonics. And my current is still the class B current, which is half sinusoid current. So current is half sinusoid and the voltage is square. And by doing that, we further decrease the overlap between these two waveforms, and I can hit theoretically up to 90.6% efficiency. And interesting thing to be noted here is that if you calculate, like since we have the Fourier coefficients for voltage and current, so for example, in this case, my fundamental voltage component is 2 divided by square root VDC minus VD. And if we divide it by fundamental current, which is like Im over 2, so if we calculate that, we get ZF naught as 1.15 times ZFV, which means that when we have changed harmonics, our fundamental has also changed from the optimum class B or class B R opt. So now my optimum fundamental impedance for class F is 1.15 times R opt of class B. So any given harmonic, when we change in load pull, the fundamental gets impacted, and as a result, we have to change the fundamental impedance. And here ZF naught Z is actually Z1L, which is the fundamental impedance. Z2F naught is second harmonic, and Z3F is third harmonic. So next. Now, inverse class F is very interesting amplifier. If we consider, it's a very interesting PA mode, because we are limiting up to 3 harmonics. And when we limit up to 3 harmonics, we are still considering that my current, because second harmonic is open, my current doesn't have any second harmonic component, but it can still have higher order harmonics like fourth harmonic, fifth harmonic, sixth harmonic, and so on. This is not an ideal inverse class F definition, because ideal inverse class F considers all even harmonics to be open. But in this case, what we are saying that because practically it's only feasible to control up to 3 harmonics, we are keeping second harmonic at open, and we can derive this I current component by using technique shown in the paper, which I have mentioned in the slides. And if you see carefully, the current waveform actually does not hit Imax, unlike class F where or class B where our current always hit Imax. My peak value of the current here is 0.7 times Im, and unlike that, the voltage, which is half sinusoid, has a very high peak, which goes up to 2.9 times VDD. So inverse class F has a high voltage, so it's mostly suited for technologies where you have high breakdown voltages. And once you keep second harmonic open, our current also changes, and current is significantly different than class B. So if I again use the same idea of finding the what is the optimum fundamental impedance, I will see that my fundamental impedance is actually 1.7 times of that of class B. So because my optimum current value is lower, I have a higher fundamental impedance, which is significantly higher than class B, and my second harmonic is open and third harmonic is short. So inverse class of theoretical efficiency, if we use these expression, goes up to 91.07%, which is among highest among the all. And the optimum impedance is also higher. And remember, the voltage swing is very high. So it's mostly suited for 3.5 technologies like GaN, where we have high breakdown voltages. Next. So now, I mean, coming to the practical realization of things, since our device is not, again, an ideal device, we have a non-linear, we have a voltage controlled current source, which you are seeing in the center. Um, but apart from that, we also have non-linearity coming from the capacitances, like the drain to source capacitance CDS, gate to source capacitance CGS, and the feedback capacitance CGD. So now what happens is that if we try to understand all the waveform engineering which conventionally people have, just with respect to output, that I think is not complete. So because of the feedback capacitance, there is a strong interaction which goes between output and input. So basically we need systems where we can tune harmonics at the output, mainly second and third, and we need simultaneously we can also control harmonic at the input, which is second harmonic source at the input of the device. So I will be diving more into how this output and input interaction happens together. But the whole idea is that if we have an ideal sinusoid driving my device, because of the non-linearity which gets generated at the input due to the non-linearity of the CGS, as shown here in the figure, the amplitude of the different Fourier coefficients at F1, F2, F3, and so on changes. Because of that, my voltage is no more an ideal waveform. My voltage significantly changes, and that altered waveform drives the gate of my device. And depending on what harmonic conditions I have at the output, I will be changing that voltage into current. So this is a kind of a systematic interaction of output and input harmonics, which will tell us whether our efficiency can decrease or our efficiency can increase, because we have been doing load pull for a long time. And when we do second harmonic source pull, for example, we see that efficiency increases, and then there is a null where efficiency will decrease and it will increase again. Similarly, at the output, we have seen second harmonic null at the output where efficiency increases and it will drop drastically, and then it will increase again. So we will try to dive more into these kind of things, that why these happen and how we can have a better understanding of these concepts for high efficiency power amplifier design. Next. So typically, if we consider the input nonlinearity, conventionally, it has been avoided, by saying that second harmonic is short circuit. And we have that impression that anything apart from second harmonic short will decrease efficiency or decrease performance. Or there is an approach where we think that, I don't care, let the second harmonic at input be wherever. wherever we want it to be, and we are on the mercy of, mercy of the god, whether this second harmonic will fall in a right position which can help us, or it might end up being in that null region where our efficiency decreases significantly. So what actually happens at second harmonic at input, especially with respect to GaN, is very, very important. And it kind of changes the way we think about this problem, because we can either increase or decrease the efficiency depending on how we terminate these harmonics. So next. So again, why this analysis is needed, why second harmonic source analysis is so crucial, is because we need to, we are moving to high bandwidth designs, we are moving to higher frequencies. And for broadband design approach, even if we consider that we are designing a really good second harmonic termination, but there are very high chances that over frequency we might fall into efficiency null, and because of that our efficiency will decrease. Similarly, we have to understand that how this input nonlinearity impacts the output, or output impacts the input nonlinearity, and vice versa. So that is something which we will be going through in the next slides. Next. So what actually is happening at input is quite interesting, because so we feed like a input sinusoid waveform at the input, and now unlike output, my CGS is very non-linear at input, and due to the non-linearity of CGS, it generates second order, mostly dominated by second order non-linearities. So if you see in this equation, my VGS is given by VGS naught plus V1 cos theta plus V2 cos 2 theta plus phi 2. And here we are defining which if you see in the bottom equation is cos theta plus gamma cos 2 theta plus phi 2. So it's very important to understand gamma and phi 2, because I will be talking about gamma and phi 2 all through these slides. So gamma is the ratio of second harmonic voltage to the to the fundamental voltage component. It's the amplitude, basically the absolute value of how much second harmonic nonlinearity is generated at the input of the device, divided by what my fundamental voltage is. And phi 2 is the phase difference between these voltage components. So at input, when we are basically doing load pulling, or we are trying to understand the phenomena, both things are changing. The gamma is changing, which means the magnitude of V2 and V1 is changing, as well as phase is also changing. The second order, the phase difference between second harmonic voltage and the fundamental voltage component. So both of these determines basically what happens with my waveform. And if you see in the bottom figure, ideally I want a sine wave, but depending where my second harmonic source termination is, I will alter my waveform drastically. Next. So what actually controls this gamma and phi 2? And this again is related to our second harmonic source pull, where when we are changing second harmonic source pull, or we are doing second harmonic source pull, what we are basically doing, we are changing gamma and phi 2. So what happens is that this gamma and phi 2 changes as a function of second harmonic source pull, and that impacts the waveform at the gate of my device. So if you see in this figure, the gamma kind of increases up to 0.6, then decreases. So 180 is like kind of short, and ideally it should be zero, like gamma should be exactly zero. But in practical world, the gamma kind of increases up to a certain point, say for example in this case up to 0.6 for some phase angles of second harmonic source, and then gamma decreases. And similarly, my phase, which is the phase difference between second harmonic and fundamental, is 180 degrees for majority of the time, but it also makes like a sharp increase, and then it decreases. And this variation in phi 2 is also important to understand, because this will change my waveforms, and it will change if my gate waveforms are changed. It also means that when this gate voltage gets converted to the current, that will also impact my performance of a given device. So next. So one thing very interesting here is that it's not that gamma and phi 2 are always harmful for our designs. The way we control second harmonic source, and that's why a lot of second harmonic source pull is needed to understand these concepts. So depending on what your phi 2 is, as I explained, like phi 2 can vary between any, it can be any number. Like theoretically it can be, I can sweep it from 0 to 360, but in a practically in a given GaN device, it makes swings from 180 to like 330 degrees. And depending on that, and depending on what my ratio of gamma is, which is basically my ratio of, again, v2 over v1, the magnitude of v2 over v1, my gate waveforms can either expand or contract. So for example, in this particular case, the black curve is the case where I have no input nonlinearity, which means my second harmonic source is short. If my second harmonic source is short, what I'm seeing here is that in some cases, for some gammas, for example, let's take a case of gamma is equal to pi, or phi 2 is equal to pi. So for phi 2 equal to pi, if I see my black curve and I see my red curve and compare both of them, they are significantly different waveforms. So gamma is equal to zero 0.5 here looks like that I am driving my gate of the device from a square-like waveform and not a sinusoid, ideal sinusoid waveform. So what this will do, basically, this will, if this voltage gets converted to the current, the red curve here will have a terrible efficiency because there will be more overlap between voltage and current at the output. And the black curve will relatively have better efficiency because the effective conduction angle of that waveform, when it changes to voltage, when it changes to current, it will have a, the conduction angle will be smaller, and as a result, I will have a higher efficiency. So if you go next, this is what the next slides explains. Go back.
Yep, sorry.
That either conduction angle expansion or conduction angle contraction phenomena can happen depending on what my gamma and phi 2 are at the input of my device. So on the left hand side, if you see the conduction angle expansion phenomena, for the voltage here is basically converted to the current. And if you see, for gamma is equal to 0.5, my waveform has a higher, my waveform is broader. If my waveform is broader, it means it will have a higher overlap with my voltage. If it has a higher overlap with my drain voltage, my efficiency will be lower. On right hand side, if you see now phi 2 has changed. For example, in left hand side, my phi 2 was out of phase. On right hand side, my phi 2 is a different phi 2. And for that, if I compare, for example, the red curve, which is gamma is equal to 0.5, my conduction angle actually significantly reduces as compared to the black curve, which is ideally class B drain current, where I have 180 degree conduction angle. Now for the same given bias, my actually conduction angle has reduced, and my conduction angle of the red waveform is significantly lower than the conduction angle of class B waveform. And similarly, if I see for another phi 2, there is a chance that that my waveform shaping happens at the input, and my effective overlap between voltage and current will decrease, and because of that, I will have a better performance. So setting the basis of this idea of conduction angle expansion and conduction angle contraction at the input, which is just dependent on the input nonlinearity and where you are biasing your device. So far, we haven't talked about output harmonics or how output will change all these phenomena, but this is a basic understanding that how conduction angle and waveform at input will change, and due to which our performance will alter, and we will have different results and interpretations depending on how we play with the output harmonics. Next. So let's start with the fundamental and the basic idea which we all are well aware of, like class B. So again, applying this gamma and phi 2 idea, so let's observe the curve on the left hand side, the conduction angle, and the efficiency curve on the right hand side. So if you see, we know that for gamma is equal to 0, which again repeating, the gamma is the ratio of second harmonic voltage to fundamental voltage component. The If you go on that axis, you will see the conduction angle. This is the change in the conduction angle, what I'm plotting here with respect to gamma and phi 2. That altered conduction angle is 180 degrees, which means if there is no input nonlinearity, which means gamma is equal to 0, I expect class B conduction angle to be 180 degrees. So if you see the right hand side, that point corresponds to 78.5%, which actually I should have shown here. But if you take gamma is equal to 0 on y-axis and go to phi 2 of 180, so this curve is 75. So that curve will be like 78.5% here. Yes, exactly where this pointer, where Vince is pointing out. So that we know and we are well aware of. But what interesting is, if we move to the left part again, and we start changing our gamma for say phi 2 is equal to 180, you see our conduction angle expands from 180 to 220. So this is like a very bad region. So if you again come on the right hand side, similarly, if we are on phi 2 equal to 180 and change gamma, my efficiency tanks and my efficiency goes from 78.5 to 60%, which all of us might have seen when we do second harmonic source pull. This is a common phenomena which we see that efficiency, we have certain efficiency, then it suddenly tanks and then it will increase again. At the same time, if we go back again to the left curve, if we have a phi 2, which basically is between 180 to say 360 degrees on the right hand side, I can actually contract my conduction angle. I can change my conduction angle from 180 to 170, 160, 150, and so on. And on the right hand side, if I see my efficiency, I can actually have a higher efficiency than 78.5. So theoretically, I can actually achieve 85 up to 85% efficiency at maximum efficiency condition in class BPA mode. Just one thing here, the second and the third harmonic in this particular case is short. So basically it's a tuned load amplifier where second and third are short, and I am only changing input nonlinearity by fixing second and third harmonics at the output to be short. So when we are doing it, there is a beautiful correlation between conduction angle expansion and contraction and change in efficiency, depending on what gamma and phi 2 my device basically have, and that my gamma and phi 2 are coming from the nonlinearity of CGS. So there is a possibility of having really, really high efficiency in class BPA mode. So now because now, I mean, we have tuners which are capable of simultaneously tuning second harmonic source as well as second harmonic load and third harmonic load at the output. So what's interesting to study here is that let's go to class F and class B. So class B and F are very similar amplifiers. The only difference between two is that third harmonic is open, which means current is still the same, but I have changed the voltage to a square like voltage. And going back to the similar analysis which we were doing in the last slide. So if we see class F at 180 degrees, and I'm changing my gamma from 0 to 0.6, my efficiency tanks. So from 90.6 theoretical efficiency, I will enter into a very bad region, which is like, 70% or below that, like 65%. And people have seen this, like
Oops, sorry.
in class F, our efficiency delta is actually higher. And again, remember that all this has been plotted for optimized fundamental impedance, that whatever you do, if input nonlinearity is there, and even if you optimize your fundamental, you won't be able to regain back your efficiency. So class B and class F, their efficiency significantly tanks with input nonlinearity. But then inverse class F, which is very interesting here, is that you have complete immunity. So if I am at 180 degrees and I'm changing my gamma, my efficiency doesn't change much from 91% to 89. And on the right hand side, if I see, I can still have some efficiency benefit. I can go up to 92, 94. That depends how much phi 2 is getting generated, which is not in our hand because that is determined by CGS and the given nonlinearity of the device. But the very interesting phenomena here is that inverse class F becomes immune to input nonlinearity. And we didn't, I mean, this is not very obvious, but when we do advanced mathematics and we have like lines and lines of codes which we have written to understand these behaviors and Fourier components. Uh, and you will see that we kind of theoretically we can predict that inverse class F efficiency will be basically immune to any sort of input nonlinearity. So next, so Vince, are we good on time? Like how much time is left?
Yeah, we're 30 minutes in, so we have time. That's fine.
Okay, so now I'm showing some practical examples of it, because when we were doing all this theory, and again, simulation tools are very complex. Like, you know, if I want to do all this, for example, Vince, if you go back, if I want to plot those kind of curves in like use ADS for them, it will take forever, because that means that for every given second harmonic, I am doing a fundamental load pull. And then when I have a fundamental load pull, I'm trying to see what my second harmonic at load is, and then fix that load and redo fundamental and then plot those efficiency numbers. So that becomes very complicated and a tedious task. So we decided to validate all this using focus go next harmonic tuners. And the idea was again like to basically relate our theory, like our gamma and phi 2s, with the measured performance and the waveforms. So here, let's take an example of class B. In class B, for a second harmonic and third harmonic short, the maximum efficiency for class B is at a non-short termination. So short gives me 71%, but there is a maximum efficiency point around 74.38 or 75%. And then there is a minimum efficiency, which is efficiency null, which can go up to 44%. So the basic, the basic point here is that, again, what is happening here at the minimum efficiency point, my gamma and phi 2 are basically shaping the waveform in such a way that my expansion of conduction angle is happening, and that significantly impacts my performance. At maximum efficiency, again, my gamma and phi 2 is changing in such a way that my contraction of my waveform happens, and due to which I have a better efficiency. And then there is a short case where I have no harmonics, no gamma and phi 2, and because of that, my efficiency is basically what I expect for a class B amplifier. So if we are designing a short termination, that is not the best possible ideal solution for class B type of amplifier. So moving next, let's see class F. Again, I mentioned this thing that in class F, we have, sorry, it behaves more like class B. And so here we are showing, again, this is under compression. I have a case where it is short, maximum efficiency and minimum efficiency point. So at short, I have some efficiency, which is around 88%. Then at maximum efficiency, it's around 91%. And if we go further, you know, there is this big dip. We just fall in the dip and we are gone. Like boom, like efficiency is gone, and we have really, really terrible efficiency. So what this is showing, and if you go on the right hand of the Smith chart, which is kind of a green area, efficiency is still bad. Like even if I want to design in that region, that's a terrible region, considering if I'm doing like a broadband matching. So for me, the best region is what is highlighted in the red color here. That's the best region for design if I'm doing class F. And the efficiency delta is quite significant, up to 30% efficiency delta in class F. So again, the design has to be done very meticulously, and the behavioral harmonics have to be studied in a nice structured manner. And one thing which I would like to mention here is that our theory predicts all this very accurately. If I take those curves where I was showing gamma and phi 2 variation and power and efficiency variation and maps them to a Smith chart, I can predict what this load pull is showing, which we are also proud of, because that is a lot of rigorous maths. And some of our papers are, that's why, difficult to understand, because it talks a lot about mathematics, but at the same time, our approach has been that we show some maths, then we have load pull as the intermediate step to match our maths closest to the device as possible using load pull. And then we go and apply those principles to design high power, high efficiency, high frequency amplifiers. Next. So now inverse class F, as I mentioned, is very interesting PA mode. You see, you have complete immunity. You go and do a load pull. We have measured high efficiency as sorry, up to 90%. And if you see here, the efficiency immunity is significant. I mean, I can pick up any region here, and it will ensure me that my efficiency is actually really high, and my efficiency doesn't change much when I change my second harmonic source termination. So this is something which is kind of very surprising, and people have a reaction to it that we don't expect this, and it is happening. And again, fundamentally understanding this, when we have second harmonic open, any input nonlinearity of second order at input basically does not impact our performance that much. One caveat here is that we have to be careful that our fundamental impedance here is tuned to the not at R opt of class B, but R opt of inverse class F, which I showed in the previous slides. It's significantly different from R opt of class B, and it's a higher fundamental impedance. So moving next. So now, I mean, I can do so many things. We can have a full sweep. So let's take example of continuous inverse class FPA mode. And one thing which I would like to, before explaining this graph, I would like to point out here is there have been a lot of papers on waveform engineering. Sometimes things can be misleading because we cannot just randomly shape voltage or randomly shape current. So for example, in class J, we do voltage shaping and not current shaping. Why? The reason for that is my current is already hitting Imax all the time because it's a class B current. But inverse class F, I showed you in previous slides that inverse class F current is significantly lower than the Imax of the device, which means that it gives me room to shape current in inverse class F and not in PA modes like class B or class F. So here, what I'm showing is if I go and tune my second harmonic load near open and enter into continuous class F PA mode, second harmonic source variation is also consistent, which means that if I am designing a broadband match in an area in like yellow and dark yellow region, I should not be worried about anything. It gives me like that immunity. It gives us immunity to fight against COVID, basically, which is like the input nonlinearity in this case. And I have I can achieve really high efficiency all throughout my band. So these are some measured gain and efficiency profiles for different termination. I mean, we can go a lot into these data, but I'm explaining this through charts that we can, of course, all this is related to gamma and phi 2, which we talked about. So for continuous inverse class F, when we are doing a broadband design near open, the input nonlinearity phenomena is also consistent. Next. But every good things comes with more problems. There is no end to that, oh yeah, this is the best thing and we know exactly now what we have to design. So I'm sorry, the legends are missing in that figure. Vince, is it a PDF or is it PPT?
It's a PowerPoint, yeah.
Okay. So here, what the first figure is showing, red curve is class C. Blue curve is basically my class J, class B, class F. All these classes we know shows nice AM profile, and that's what we want, because for advanced modulated architectures, I don't want my AM to be bumpy. So it will be a big problem when we go to systems like digital pre-distortion, and it will be super hard to linearize such systems. So this phenomena was first time predicted by our work on the double inflection characteristics. It's very interesting that in inverse class F, unlike other PA modes, there are double inflection phenomena which happens, due to which my AM is very bad. And people have made this comments in the past that the basically the the inverse class F is a saturated amplifier, which means that inverse class F is good for application which doesn't require any P3 dB, for example, compression idea. So people use it for applications like, you know, heating, or for other applications like which are non-cellular. So the point here is that if what I have shown in the previous slides is true, that, you know, which I was saying that, yeah, inverse class F gives immunity to nonlinearity, then when I show this slide to you guys, then it means that, you know, this is just terrible, because this PA cannot be used for cellular application. So when we discovered it, we also have measured this, and this is also shown in the basically in the simulations. So if you go next, Vince. So any model you take, there are different models available, equation-based models, whether it is Pedro's, a Yang model, a Fager's model, and you try to make your own device like current source model. All of them consistently shows terrible AM profile for inverse class F or inverse class F like PA mode, which means that if I'm tuning near open, you know, I will definitely get bad AM characteristic. Unlike class B, you know, if you see the grave curve, it's nice and smooth. There is a soft gain expansion, and then gain compression happens. But for other PA modes like inverse class F, you know, these are very bad AMM, and it also means that my P3 dB efficiency will be really bad here, because just because of the AMAM phenomena, when I splice this data, my efficiency will be lower than the peak efficiency. I might get very high peak efficiency, but my P3 dB efficiency will be very bad, and we don't want that for cellular application. So what's the reason for this, and what's the solution to overcome that I will be showing in the next slide. So Vince, can you play this animation first? So what this animation is showing, which I think is very interesting, that the AM for the red curve is bad. You know, it's going under 10 dB compression. And if you look at the load line for red curve, stop. Can you? Okay. So if you see the red line for the load line for the red curve, and this the red curve hits the knee region very early in power range, which means if you go back, yes, go back, yeah, exactly. So which means that for red case, my load line is hitting my knee region at a very early power, and blue curve on contrary shows the normal compression phenomena, and it hits my knee region at the higher power level. So what does this mean? This means that we know the compression starts when load line starts hitting the knee region, right? This is like the basic understanding of the load line interaction with the knee region. So in the blue curve, that compression starts at high power level, which we are used to seeing, and we know for class B, class AB amplifiers. But for inverse class F, my knee hits the my load line hits the knee region even at lower power levels, which is terrible, because it means that my device is always under compression for inverse class F. So this phenomena, we understood it, we mathematically predicted it, but now the beauty is that by input gamma and phi 2, I can change this phenomena. I can change where my load line will actually hit knee region, and it's the same PA at the output, but by changing input nonlinearity and playing with the input nonlinearity, I can change the same PA from red curve to the blue curve. And my efficiency will be, again, it shows less than 3 dB compression. My efficiency will be really good, and I don't have to worry about any inflection in my AMM curve, because when I will take this part and design like a Doherty, I don't want any bumps or any kinks in my AMM profile. So input harmonic tuning actually helps in AMM enhancement, and we have shown this extensively. And this animation, people find it very interesting. We presented it, my colleague Jeff Roberts, he presented it last year in IMS, and a lot of people had requests. So I posted it publicly on my LinkedIn page, and you can download it from there if you want. So if you go next, so yeah, like this is the interaction which happens and which changes the idea of how things happen in inverse class F mode. Next, Vince. So with this, I mean, with this, the fundamental idea and explaining all this input nonlinearity phenomena, this is what I wanted to share today with you guys. And Vince might be talking about some of the PAs we have designed at high power, low power, and at even millimeter wave here, where we are applying all these phenomena. So on the left hand part, low power mode, low power, which is 40 dB, and which is like 310 watt PA modes, which is very popular in academia. Cretan what device we have used here, and we are showing reasonable bandwidth. But then we have been doing a lot of waveform engineering for high power application for 50 dBm and more, and we are able to pretty much match our theory, our load pull, and our performance of the parts using that. And similarly for MMICs, we are playing up with this input-output harmonics and applying those principles to basically achieve high efficiency and high performance using the understanding of simultaneously input and output design. So with that, I think I will hand over it to Vince, and he will talk some of the focus stuff which he has been working on lately.
Yeah, thank you, Tushar. Very good explanation, thorough explanation of these, principles. And like I mentioned earlier, we've had a lot of people, customers, tuning second harmonic on the input for years with a very basic understanding or not understanding the concept at all of what the effects were. They saw the end result, but couldn't really wrap their mind around it. I remember we presented this paper at European Microwave last year, and before that presentation, I had a talk with Paul Tasker. So his category of people that can understand that, I think, is limited. He was able to wrap his mind and understood this very well. I think most people kind of do it trial and error kind of a thing. And here's just a quick example. Here's a measurement we did on the right of a second F0 load pull we did, and looking at harmonics. And you can see that the efficiency here, the difference from the maximum to the optimum point is like 39.9 to like 41. So you get like roughly 1 to 2% variation. So, this is the typical customer that does this, wants to optimize the efficiency of his PA and only gets a few points of efficiency. But then when he starts tuning the source impedance, he gets a huge variation. Now we're, if we look at the max, you see 41 versus 42. So that's maybe not a huge increase, but you can see that if you're not careful, you could hit very, very deep points where you basically kill your efficiency significantly. So now, and this is an example with this a measurement we did at fundamental 30 gigahertz. So this is a second harmonic tuning at 60 gigahertz. So we're seeing this more and more, not just at the 2-3 gigahertz applications, but at the millimeter wave as well. So again, we're kind of a bit above our time now, so I'll just go quickly above this. But again, these are topics we've covered a bit yesterday, but here are two simple examples of like an 18 gigahertz and a 67 gigahertz system. So you see here that the main difference that you've seen is this phase reference. So obviously we can't just use a normal vector system. We need a vector receiver system to look at the A and B waves and characterize them adequately, but you also need a phase calibration in the setup. So again, if we look at a live setup, what this looks like, we showed this yesterday. So this is like a 0.8 to 18 gigahertz system that basically controls not only the fundamentals, but the harmonics as well. Same here with this is an example of a 10 to 67. So if you want to do like, 5G design where you're actually tuning at like 28 gigahertz and controlling the harmonic up to 56 gigahertz, in some cases higher. Well, in this case, you could do it with these kind of setups where you have harmonic tuning both on the input and on the output with passive tuners. And again, it all ties in together with what we call this phase reference. And basically what this does, this is a pre-calibration that we do at the factory, and it basically correlates the difference between the phase variation between the fundamental and the harmonic frequencies. So we do this calibration ahead of time, and then we ship it to the customer, and then there's just calibration steps to make this right. So then when we actually measure the A and B wave, all of it is correlated and makes sense. So for example, this is taken from Keysight's PNAX data sheet, but basically just kind of gives you an example. We stimulate the device that's inside the phase reference, measure the response, and as you can see over time, here's an example of one, and this is the phase variation over multiple hours. So we do this long time calibration and see what the variation is in that phase variance. So, and at the end, what this allows us to do is when we do all these load pull and power sweeps, it allows us to gather tons and tons of data, and then we can slice this data and actually look at the current and waveform as we move along, and select the impedances, the combination of impedance that will allow us to hit these kind of waveforms that will define the class of operation and get us to the these phenomenons and theories that can be applicable in real life designs. So again, we're maybe 5 minutes past our time. So, I want to open it up for Q&A. So I guess Remy's been monitoring the session there. So maybe Roland, you could open up Remy's mic so to see if we can tackle a few questions there.